Hi everyone. So nearly at the end of the course, just two topics left. Here we go then, binomial expansion. What's the point of it and where does it come from? So we're on C2 again. And essentially, what's the point of binomial expansion? Well, the point of C2 binomial expansion is to avoid you multiplying out loads of brackets. But the actual binomial expansion really is, again, in your second year, is C4, and it's used to approximate curves. Okay, so in other words, how does your calculator know what root 2 is? Well, it puts it into a binomial expansion. It puts it into the equivalent of actually, let's change that. So let's say it wanted root 2.1. What would that be? So that would be put into an expansion of this curve here, which would expand into a polynomial. So it would look like 2 to the half, 1 plus x over 2 to the half. So it would be root 2, 1 plus, and it would look like this, etc. Okay? And that, if you whack in x equals 0.1, can you see 2 plus 0.1 gives you 2.1, will give you an approximation for that curve. Now this seems quite abstract at the moment, and it will because we're not on C4 yet, but that is primarily what binomial expansion is used for. It's how your calculators find approximations to curves. So that root 2, that is an approximation. Root 2.1 is an approximation that your calculator is using. We're not at that point yet though. We're at the C2 binomial expansion, so the simplified version. And like I say, the C2 binomial expansion really prevents you from expanding out loads of brackets. And we're going to build, it's a formula essentially, and we're going to build it. Okay, so let's try this out. So a plus b all to the power of 0, as we know, anything to the power of 0 is 1. A plus b all to the 1. This is the same as 1a, isn't it? Add 1b. You're going to see the point of this in a sec. What about a plus b squared? So if I expand that out, that's a squared plus 2ab plus b squared, isn't it? So this is the same as 1a squared 1a squared plus 2ab plus 1b squared. Yeah. A plus b cubed. Oh, we're starting to see why this is such a pain, because I don't want to have to keep expanding out brackets. I already know a plus b all squared is that, so now I need to times that. So that's a cubed plus 2a squared b plus ab squared plus ba squared plus 2ab squared plus b cubed. So this gives me a cubed, that's that one. Any more a squareds? Yeah, that one. So plus 3a squared b plus 3ab squared plus b cubed. So this goes to 1a cubed plus 3 lots of a squared b plus 3 lots of ab squared plus 1 lot of b cubed. And then, if we continue, a plus b to the power of 4. Oh, do we want to do it? No, I don't want to do it. Okay, I don't want to expand it out. Do you see? This is why we have the binomial expansion. What if I put a plus b to the 5, to the 6, to the 100? You're not going to expand that out every time, are you? We have to have something more rigorous, and that's where maths comes in. Right? Now, some of you may see a pattern here with these numbers. So I'm always torn between how much I should go through binomial expansion with people. I mean, we could really go to town on the detail of this. I really like talking about it, but from experience, I noticed that students' eyes tend to glaze over a bit when I go into too much detail, so we'll do a compromise. We'll go half and half. Can you notice that the coefficients of these numbers, so remember the coefficient is the number next to, can you see this looks like and is what's called Pascal's triangle? Okay, so Pascal's triangle, I can clearly see there's ones along the edges, so 1, 1, and it's a triangle, and it's symmetrical triangle. And what's happening every time, you can see that this number plus this number, whatever falls in the middle gives you the next number. 1 and 2, whatever falls in the middle gives you 3. So 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, 1. Do you see? And it's symmetrical, isn't it? It's symmetrical about that halfway number here. Notice then that if I expand all the brackets, if you give me, so a good layout here, this is to the power of 0, isn't it? A plus b to 0. This one's to the 1, 2, 3, 4, 5, and 6. So if you asked me what a plus b to the power of 6 was, I would be able to tell you. I would be able to tell you that it's 1, and now, so let's do it. A plus b to the 6. We can see a rough pattern here. We know the coefficients, so I know I'm going to have 1, 6, 15, 20, 15, 6, and 1, right? 1. But what about the A's and B's? Can you see what's happening here? A. This is a to the 1 times a to the 0 here, isn't it? A to the 0 is 1. You see this is a squared times b to the 0. There's a b to the 0 here, isn't there? These illusionary things, 1, 1, and this is 1a to the 0, b squared. Can you see this is b to the 0? This is b to the 1, a to the 1, and this is a to the 0. Do you see? I feel like an MC at the moment. So can you see what happens to the powers of A? The first object in that bracket is reducing its power by 1. So A to the 1 goes A to the 0. So I know that this is going to go A to the 6, A to the 5, 4, 3, 2, 1, and 0, right? And also this plus B, B 0, 1. 0, 1, 2. It escalates in power, doesn't it? So b to the 0 is the first thing. B to the 1, b squared, b cubed, b to the 4, b to the 5, plus b to the 6. Plus, 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 plus. Do you see the simplicity of it? I can just add and you can just see the pattern, can't you? You can see that the power of A reduces by 1 every time, and the power of B increases by 1 every time. But what we need is a general formula, don't we? Can we see that this can be applied to anything? So A plus B, if I go onto another page, so if I had A plus B to the 10, all I need to know is my Pascal's triangle 1, 1, 1, 2, 1, 3, 3, 1, 4, 6, 4, 1, 5, 10, 10, 5, 1, 20, 15, 6, 1, 7, 21, 35, 35, 21, 7, 1. Do you see? I can just keep going, can't I? But again, this doesn't seem very efficient, because it's definitely sped up time, but I have to draw this triangle every time, don't I? You know, I could do it, but I don't really want to do that every time, and that's why we need a generalized formula. So what is the generalized formula? If we do it on this one. So the general formula general formula. The general formula is if you have a plus b to the power of n, this is the same as n choose 0, a to the power of 0, sorry, a to the power of n, b to the power of 0, okay, plus n choose 1, a to the power of n minus 1, b to the 1, plus n choose 2, a to the power of n minus 2, b to the power of 2, plus n choose 3, a to the power of n minus 3, b cubed, plus dot 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 dot, plus any, let's say the power was r this time, so it's going up to the power of r, so n choose r, a to the power of n minus r, b to the r. This is your general formula, okay? And as this thing's symmetrical, because in C2, this value of n is for positive integers, okay? In second year, it will be fractions and negatives, so this formula won't be able to apply. And that's why I always hesitate whether I should bother teach you this, but it is useful in further maths, so it's important that you know this. Now, what does this n choose mean? So this formula, this is what you have to remember. This formula, it's a lot less complicated than it looks. What does this n choose thing mean? Well, I think first, let's actually just do an example with it, and then we can go back, okay? Because I just want you to see how simple it is, really. So if we're expanding an ascending order of powers of x up to the fourth term of this, so a simple one, we could change that actually. Why don't we change that to the power of 10? So let's change that to 10. Bring that power up. Okay, and let's see the formula in action then. You can just do this with your calculators. So 1 plus 2x to the 10 is the same as, from our formula, n is 10 here, so n is the power. So 10, choose 0. A is 1, so 1 to the power of 0, 1 to the power of 10, and then 2x is our b. Notice I'm putting the whole of it in there, because if that was minus 2x, then in here that would need to be minus 2x, okay? So 2x to the 0, plus, and because it wants the first 4 terms, so we've got to do this 9, so taking 1 away from that power, 2x to the 1, plus 10, choose 2, 1 to the 8, 2x squared, so that's 1, 2, 3, and then our fourth term, choose 3, 1 to the power of 7, 2x to the power of 3, and then dot dot dot. You can now just go to your calculator. So 10, choose 0. I know this needs to be 1 from Pascal's triangle. I know that, don't I? We've done that. So that choose button is your shift and then on your divide, I think. So 10 choose 0 is 1. 1 to the power of 10 is 1. 2 to the x, 2x to the power of 0 is obviously 1. Plus 10 choose 1. And if you are on it and you saw in that Pascal's triangle, the next number, if we go back, is the power that we're looking for, isn't it? These are the powers, 7, 6, 5, 4, 3, 2, 1, of a plus b to the power of n. So 10 choose 1 in your calculator is just 10. 1 to the power of 9 is 1. 2x to the power of 1 is 2x plus 10 choose 2. Calculator. So you just literally write 10, shift divide, and then 2 equals. So 45. 1 to the power of 8 is 1. And then you got your 4x squared. Plus 10 choose 3. 10 choose 3. 120. 1. 2 to the x is 8x cubed, isn't it? Because it's all cubed. Plus dot dot dot. So your finished answer is 1 plus 20x plus 45 times 4. So 180 x squared plus 120 times 8, 960 x cubed. And we would never leave that. We need to check. So we're going to check. We never walk away from a binomial not knowing that we're right. Binomial, if you see a binomial on your exam, you just like score. This is easy. It's easy. So check by putting in 0.01 in your x value, right? So put 0. So left hand side, 0.01 into there. So 0.01 answer, 1 plus 2 answer, all to the power of 10. It is 1.218994442. If I whack it in my right hand side, so in other words, my expansion, right? And remember the dot 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 because it goes on all the way up until x to the power of 10, doesn't it? So 0.01 answer, 1 plus 20 answer plus 180 answer squared plus 960 answer cubed. I get 1.21896. So, as long as we are correct, yes, cool. We should be correct to 6 values, the first 6 values. This is a weird one. We should be right to 60p because 0.01 all cubed will be, if you cube that, you're going to get right to 60p. But as the right-hand side doesn't go to 60p, that's why it's not exactly going to match this time. But in general, it will always work. Weird to pick an example, it doesn't work. But you can see how close that is. Definitely exactly the same to 5 significant figures. I would expect it to be 6. So alarm bells aren't quite ringing really. I think that's okay. Okay? That is it. That is binomial expansion, the basics. But where and why does this happen? So why does this happen? What is this 10 choose 0? What is it? What is this n choose r business here? And this is the bit I want to focus on. I mean, it's obvious why the a and b, their powers are decreasing and increasing. We can see that, can't we? We can see the pattern. But what is n choose r? This is important. So what is n choose r? Because this is something that you could get picked up on in terms of theory questions, and it's important for you to understand. This means that's C, so that means choose, okay? So this is called theory of combinations, which is why I've written it up here, but I'm not going to go into massive detail about it. What is n choose r formula? Well, this is n factorial over n minus r factorial times r factorial, all right? This describes every single coefficient within that Pascal's triangle. And what this so there's lots of things here to address, isn't there? What is factorial? What does that mean? Well, factorial means number of permutations. So let's say I have 4 different seats and 4 different people, yeah? Can you see that if I want to fill this seat here, there are 4 choices to pick from, aren't there? There are 4 people to choose from. So let's say this person goes there. So at the moment there are 4 total. There are 4 combinations. Now I've got 3 chairs left, 3 different people, 3. So there are 12 different ways so far. There are 2 chairs left. I've got 2 different people to choose from. And then there's 1 chair left, so I've got 1 person to choose from. So 4 factorial means 4 times 3 times 2 times 1. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Do you see? It means number of permutations, number of ways of, if you've got 10 seats, you've got 10 people, how many different ways can I fill those seats? All right? So that's the first thing. What does this n choose r mean? Well, this means how many different ways are there, unique ways of picking certain objects from an overall number of objects. So, for example, if I had an apple, an orange, a banana, a pineapple, and some cherries, let's say. Okay. Some cherries. You draw cherries, whatever. Cherries, okay. So apple, orange, banana, pineapple, cherries. Make it easier using letters. How many different ways? So if I wanted to say there's 1, 2, 3, 4, 5 different objects, yeah? So there are n equals 5 here. There are 5 different objects. How many ways can I uniquely pair up these objects? That's what n choose r mean. This is saying 5 choose 2. Okay? So let's do it by hand. So apple can go with orange, apple can go with banana, apple can go with pineapple, apple can go with cherry. Orange can go with banana, orange with pineapple, orange with cherry, banana, pineapple, banana, cherry, and pineapple and cherry. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different combinations. Yeah, there are 10 different unique pairs. So orange and banana orange are just considered the same pair. So this is 10. If you go to your calculator, n choose r, so 10 choose 2, sorry, 5 choose 2, you do get in fact 10. Fantastic. And let's see that in action with our formula that we've written here. So 5 choose 2 is the same as n factorial. So n, remember, was 5, so 5 factorial, all over n minus r, so 5 minus 2 factorial, 3 factorial, times by r factorial, and r, remember, was 2. So, can you see, we can write this out a lot easier. There's some really fun stuff you can do with factorials. Can you see that 5 factorial is the same as 5 times 4 factorial? Can you see that? And 4 factorial is the same as 4 times 3 factorial over 3 factorial, 2 factorial. And do you see that 3 factorial cancels out? 4 divided by 2 times 1 is just 4 divided by 2. So there you go, you're left with 10. How does that relate to the context of binomial expansion? Very briefly, this can be applied to your a plus b cubed, for instance, because it's saying a plus b cubed, how many combinations are there of making a cubed or b cubed or ab or ab squared? Do you see? That's where the kind of logic fits in, but I don't want to go too far with this, and we can do another examples video after this. Okay.